Okay, let me check to see if I'm up. Sure, yeah, restore, because that was stupid. Okay, I'm sorry about that, guys. I was in the middle of streaming, and somehow I thought it was appropriate for me to press the power button on my computer. I don't know what happened. Let me see, am I up? 1 second. I'm terribly sorry about that, guys. That was a complete and total accident. Let me see, am I good? The volume's out. I'm really sorry. I had been using a Razer Naga for the past few days. Here, let me go ahead and reset that terminal on the left. I've been using a Razer Naga for the past few days because, well, the Naga has a number pad on the side and things like that. But the Naga has a double clicking issue and it kept freaking double clicking. And so what I did is I decided, okay, well, I remove the Razer Naga from my computer. What happens to be plugged in on the front of my computer for one reason or another, and as I was starting to remove the USB, my pinky accidentally pressed in the power button because I needed a little bit more leverage, and I turned off my computer. So yeah, that just happened. Okay, let's go ahead and CD into projects. Simuleos, Huffman, getting back to it, CD, projects, Simuleos, and Huffman. Let's go into vitter.cpp. And let's continue as if nothing had ever happened. Yep, that's me being an idiot. Okay, so obviously the stuff that we just wrote was not written because... Yep. Okay, so let's go here and let's create a function to test to see whether a new character is in the tree. Okay, so what do we want? It's going to be Boolean in tree. Oh, I can't believe I did that. I've been streaming for like a year on and off, and I have never done that before. I've never just... Every once in a while my computer will turn off because I'm you know, it's just using up too much power or something like that. I don't know, but never have I accidentally pressed the power button. That was new. Okay, so void entry, what do we need? We need std vector of node star internal, and of course we need what do we need? Character new key. Okay, so let's take this and let's put it down at the bottom. G, oh, G. And let's just go ahead and copy this comment up here. Yep. Okay, good. So let's go here and let's write the function. So void entry vector node of internal nodes. And just for the record, guys, in case you're wondering, it is an absolutely beautiful day on this lovely island of Okinawa. I don't know what temperature it is. It's just a nice day. It's like always a nice day. Yes, I know, ampersands, thanks. Okay, let me go here. I have accidentally removed a character that I needed. Ampersand. Up to the top, add an ampersand there. Good. Now we go down to the bottom. Okay. So, what do we need? We need to basically return whether the, whether it's in the tree or not. So we have our vector of internal nodes. You know what? I'm gonna do this a slow way, a super slow way. Maybe there's a way. If we have the vector, now I'm gonna do this safe. It's gonna be slow. I'm gonna do it safe. So we're gonna say Boolean value. I don't know. I don't know what to call these. Is it in the tree? I guess is in. Kind of makes sense. I'm sorry, my naming is awful right now. Boolean is in. You're right. We should be checking external nodes. And thanks for catching that, Zadiston. External, and go up here to external. Okay. Boolean is in. So what we're going to do is go through each of the external nodes that we have so far, and checking to see if the new key is in one of those or not. So we're going to say for auto. What did I call it before? Element. Please look at me knowing how to name things. Auto element. And what do we want in external? I think this should work. We're then going to say, okay. So now we're going to say for auto element, we're just going to go through all the elements. There aren't going to be that many elements at max. Like, I mean, the absolute maximum, if we use all the characters we could, is going to be like 100 or something like that. This is one case where find if would result in more concise code. Yeah, I've never used find if before. That's fine. This is the first time for everything. Find if, let's see. I know Gustorn just used it, but I just have not used it before. Okay, so what do we have? Find if my vector begin, my vector end is odd. Where's is odd defined? Sorry. Boolean is odd. Return. Let me see. Return I divided by 2 equals 1. Okay, so what we'd want then is we want to return, yeah, I'm really bad with lambda functions. Okay, let's see if we can do this then. So, we need a function to check to see. Okay. Any particular reason you're not using syntax highlighting or in smart indentation? Well, smart indentation drives me nuts, and so does syntax highlighting. That's why. That's literally the only reason. I know it's weird. I get that, but what was that command again? Which command? Oh, I don't remember. Let me think. I think it's this one. Yeah. Okay. What do we do? Yeah, that was the one. Okay. So we've already used find if before in a very similar way. This was actually written by Gustorn and Zadison, mainly Gustorn. So what do we want? We want to return find if beginning and internal block member node n, and we return weight equal block member weight. Let me see. So we're basically going to be using a very similar thing here. So we go through the entire list of internal and external nodes, or in this case, external nodes. And then let's see, block member. Where is block member defined? 1 second. Block member. Oop. Block member. Nope. Block member. There we go. We're reading in block member. Of course we're reading in block member. Okay. So what we're saying is we'll return n with node n. Okay. So I'm going to take this and hopefully make sense of it. Okay. Let's go here. Okay. So we need to return basically a true-false statement. Is this new character that we're encoding in already in the list of external nodes? So we're going to go through here, and we're going to say begin external. Oh, I didn't need to delete all of that. And external here. Okay, block member. So we don't have that, but we do have new key. Now here's the thing. I'm really bad with lambda functions. So let's see what we need to do. Find if returns the iterator pointing to the matching element. What do the block around block member? I don't actually know. I need to learn a little bit more about this. Find if returns the iterator pointing to the matching element, or the end of the container if it's not found. Okay. So let's think. The lambda function is basically a way to read in. Okay, let's go through and take a look at some things. First of all, the find if command. Iterator, find if, my vector begin, my vector end with the function is odd. So the idea here is that we can read in, yeah. I don't need anything inside. Let me think. What do we need to do? So in this case, we're basically doing the same find if command we had before. My vector begin, my vector end, except instead of using is odd, we're going to be using the lambda function that we have before. Now, that we have here? Now, what is a lambda function? Well, the lambda function is going to need. Let me see. Where does node n? Node n must be created then. Yep. Let me go to the top. The parentheses after that, this guy right here is creating. Oh, let me see. Node n. I think it's writing a node. 1 second. Node, internal node. Yeah, so I'd have to imagine it's block member. I think the syntax is it not the same in C#? I don't know. I don't really know much about C#. But I'd imagine they're pretty similar, right? Okay. So block member. We don't have block member in this case. We have new key, and we have old key. So what we should be able to do is the following. We should be able to do. Now, forgive me if I'm wrong here. We should be able to do this pointing to key equals new key. Yeah. Again, guys, I'm really bad with lambda functions. So what I'm going to do now is I'm going to very quickly create, no. I know what I'm doing. We have this boolean in tree function. So let's write this. We already have all of our external and internal nodes, right, in some sort of vector. So let's just go through and check to see if a character that we know is in this particular encoded tree is in this particular encoded tree. So again, the phrase that we're encoding is Jack and Jill went up the hill to fetch a pail of water. So let's go down and let's do it. So checking our in tree command. So what we're going to do is, I don't know, we'll say boolean. Oh gosh. In tree check. Is it with the end of the vector? At the moment, it's dereferencing the iterator returned. What you want is to compare it with the end of the vector. Okay. 1 second. We're going to do in tree. And what do we want here? We want phrase. No, we want external, which is going to be, I think, tree.external. And we want the character J. Let me just see if this runs, and then we'll go from there. So let's make it. Okay, seems to run just fine. So now let's see what we got. And let's also just put a quick cout. std cout is using for value out of the lambda scope. I'm really bad at this. Let's do in tree check end line. Okay. Yeah, the curly brackets are definitely the body of the function that we're working with. Let's see, is the part of the parameters that lambda takes? Yep. And then let's see, the yes, is a part for the value out of the lambda scope. Okay, so let's see, what do we need here? So Edison, at the moment, it's dereferencing the iterator returned. What you want is to compare it with the end of the vector. Okay. The return value is always going to be true right now. Okay. So we're saying return, okay. Okay, so this find if. Okay, I see what you're saying. So we're not going to return this. Instead, let me see. What do we do? Find if is going to return this iterator here. Okay. I'm working on it. So let's see. First, let's check. Again, I'm really bad with lambda functions, guys. Forgive me for this. I'm going to go through and I'm just going to try a couple of different things. So let's go ahead and write this. Let's go down here and make it. Let's check to make sure first we get a... That wasn't what I was expecting. I was expecting a true or a false value, not a 1. You can add equals... 1 second. You can add equals std and external. Return find if not equal to end external. But what if... Okay, stupid question. What if the character that we're looking for is the very last encoded character in the string or in the vector? So like the vector has a whole bunch of different elements in it, and the very last element's like a K, and we check to see, hey, is the K in there? Okay, let's go through real quick. G, so we have this, find if, 1 second. So now we want the following. Oh. Okay, good. Thanks, guys. Not equal to std end of external. Bah. Node key. Whatever. I'm sorry about this, guys. Let me hear it. Let's do make. Okay. Okay, so let me go over here then. Let's see what happens if we remove a star, maybe. That one seemed to work. Okay. So let's go up to the very top here. Not very top. It's like literally 2 lines up. Yep. Good. Okay, so now let's remove a couple spaces here. Doop. And entry check. So what I want to do then is check a letter that's definitely not in there, which is going to be like a Q. Make. Good, that's a 0. Fantastic. Okay, so this seems to work then. Okay, so let's go through and let's change a couple of things real quick. Because I don't really like this at all. I mean, it's fine. It looks good, but it's just, I don't like the way it looks. It just looks bad. New key, return. We can do it this way. One second. This should be enough space to just put this here. And then I'm not gonna worry about it. Good. Fair enough for me. I don't care. Okay. So let's go ahead and write this. Make it one more time. And good. It's returning a 0 for Q, and it should be returning a 1 for J, which is definitely in the string. Okay, write this. Go over here. Make. Good. Returns a 1. And just so you guys, we are clear here, let me go ahead and add in a quick string here that is one if in, just so you guys can see in the output over there to the left. Make. Okay, so one if in, it's a 1. Q. One if in, it's a 0. Which is good. Okay, so let me get a quick sip of water and then we can keep working on it from there. And I realize, guys, we might be moving a little bit slow today. I totally understand that. Again, we were kind of off for a week. I'm still not feeling exactly better, but a lot better than I was. So forgive me if we're moving a little bit slow today. But hopefully we'll pick up pace pretty soon. Okay, so the first thing we need to do is check to see whether it is the character is in the tree or not. So we're going to go through and create our quick if statements. 1 second. So if, where are we? Entry of, let's see, we want all of our external nodes. So where do we have our external nodes? I guess we're just going to have a vector of internal external nodes. So let's go here and let's do, better yet, let's go here and let's read in our Huffman tree. Yeah, I think that should be okay. So we're going to read in our Huffman tree. So we're going to say Huffman tree. And I guess we'll just call it tree. Why not? We'll just call it tree for now. And let's add an ampersand in there because Addison will get angry otherwise. And let's go up here and add in a Huffman tree up there. So entry vitter Huffman tree. Good. Down to the bottom. Entry, and what do we need to read in? It'll be tree.external. And the character. So it's going to be phrase of I. No semicolon needed there. And I misspelled phrase. And then we put in an else statement. Okay, so this effectively... What was that? Else. And this effectively splits our system into two different, I guess you could say, paths. The first path is if the element in our phrase has already been encoded in. So like if we're on our second capital J, so Jack and Jill, second capital J, then we move along one path. Otherwise, we add a new element to the tree. So I'm going to very quickly add in some comments here. And this is going to say, what is it going to say? It's going to say element already in tree. Down here, element must be added to tree. I always screw up with casing here. I should probably keep casing the same. So let's go here, element, there. Okay, so let's go ahead and do, oh, I don't know, which one should we do? Here in the code they have, let's see, leaf to increment. If Q is a 0 node, so I guess we'll start with that one. So let's do where it is not in the tree first. Okay. So it says replace Q by an internal node with 2 leaf nodes, 0 children, such that the right node corresponds to a J. So let's go ahead and do that. We have in tree, so I guess we're going to create a new function, and this function is going to be, it's not going to be new node. How about extend node or something like that? We'll call it extend node. So function to extend the not yet translated or 0 node. So it's going to be called void extend node. Okay, what do we need? We need, I would guess, the Huffman tree. Ampersand tree. And just to make sure this is working, let me go ahead and output some stuff and run it real quick. So we're going to do std cout, and we want to say element already in tree. 1 second, end line. And then we're going to go down here and do the same thing here, except std cout element not found in tree yet. Spoiler alert, it will be in the tree eventually. So then we do a new line. There we go. And let's go ahead and create this function. Void external node. Pop this up at the very top. So where's main? There. And let's put it here. Well, actually, wait. Where did I put the other one? Here. Void extend node. And real quick, function to extend Um, not yet translated, or a 0 node. Right, this, go down to the very end here, add in a semicolon right, and let's make it real quick just to make sure. Of course, I screwed something up. That's okay. Go to 92 and add in another parentheses, which is what I forgot. Make. Okay, so it seems to still work just fine. Good. Okay, so let's go through. Let's create the extend node function. And honestly, this might be as far as we get today, the extend node function. I realize it's not that far, but hey, we're taking it one step at a time, moving kind of slowly. Again, I still got kind of a headache, and somehow I just lost my voice like a minute or two ago. I don't know what happened to it, but it's gone. It just ran away. Which is fine. It happens all the time. Okay, so what do we need to do? We need to replace... we'll replace the not yet translated node with a new not yet translated node on the left, and a external and external on the right. Good. So we have the node. How do we know it's the not yet translated node? Well, it's going to be the only. It should be the only the leader of the 0 block. So let's go here and let's write that in. So not yet translated node should be leader of 0 block. Hey Novelist, it might be beneficial to keep track of the not yet translated node in the tree struct. Actually, where does the not yet translated node go? Is it in the internal or is it in the external? Yeah, but actually I was thinking about it. The not yet translated node will always be at the end of our either internal or external vector, right? It will always be at the end of it. So I think what we should do... Yeah, you're probably right. So let's go here. vi Huffman .h. But let me think, what do we need to keep track of in the external node? Or, I'm sorry, the not yet translated node. So let me go down here to the Huffman tree. Okay, these will be used for vector algorithm testing. So we have vector node star internal and vector in external. Oh my gosh, I can't speak today. Okay, we have the vector of nodes, internal and external. What we need is also... If we keep the not yet translated node here... Okay, I'm trying to... I think... Sorry for the yawn, guys. Okay, so let's do this then. Hey, the Mad Dave, what's up? Sorry, Novelist, if I didn't say hi. I might have forgotten to. But hey, thanks for coming in. Okay. Yeah, I'm almost all the way healthier. I still have a bit of a headache, and my throat's still a little bit itchy, but hey, it's much better than I was. So I guess we can keep the not yet translated node here. So we'll say node star not yet translated. Is that it? Okay. I'll assume it's it. Okay. So we need to replace the not yet translated node with 2 additional elements. Sorry about the sniffles, guys. There's only so much I can do about it. I apologize. Okay, so what do we need to do? We need... Hey, Gallows Group, what's up? Okay, so we have the not yet translated node being set, but I'm trying to think here. I feel like we're missing something here. So if we have the not yet translated node, it's always going to be of 0 weight. So based on how we put it into our list of internal and external nodes, it's always going to be at the end of the block, right? Or at the end of the vector. So it is not so hard to find. And I'm trying to think here. If we have, let's see. If we have a list, what do we need to do here? Let's go ahead and, oh, do I not have Zernal up? No, I don't, because I turned off my computer. Zernal. Okay, so here's what we need to do. And this is kind of, feel free to give me your input, guys, if you have any input. If you don't, of course, don't worry about it. Okay, so we have a situation where, let's say we have a couple nodes here. I don't know what I'm doing. So we'll have something that looks like this. Yeah, sure, whatever. Somehow we create something like this. No. Let's keep this simple. Keep it super simple. I don't think eternal notes are in the algorithm. Let me see. Let me look. Eternal. Yep, you're right. External. Let me see. I think you misspelled. Yes, so the strange mix of C and C++. I mean, I'm a physicist. That's always my excuse. Not a programmer. Okay, so let's go through and let's think about what we need to do here. Oops, sorry about that. Okay, so what I'm going to do is I'm going to assume we have an external node here, and an internal node, 0 node here. So basically we just have one guy. Okay, so we have one guy, and he's here. Now we need to add in a new element. So what we need to do is add in 2 new elements here, a leaf node of weight 0 and an internal node of weight 0. Let me see. I mean, honestly, the thing is my syntax, though. I use C syntax a lot more than C++ syntax. It's just because, I don't know. Honestly, the code that I'm working on is always like a mix between C and C++, and it doesn't really matter that much, in my opinion. Okay. So what needs to happen when we do this? Well, we have this node. We have this node. And we have this node. Okay. This is a leaf node, so this needs to go to external. This needs to go to internal. I'm really bad with templates. I gotta be honest, like, I'm really bad with templates. I'm just now getting comfortable with overloading functions. So don't give me templates. Okay. Now this guy, the new not yet translated node, the new 0 node, I think it's fine to leave it in its own block, not yet translated. That's probably fine. Okay, so now we have the question, how do we know where the not yet translated node is? And this is what's kind of boggling my mind right now. I'm not sure how to exactly approach this problem. So on the one hand, we have this implicit numbering scheme. And the implicit numbering scheme is really useful in that we can tell where all the internal and external nodes are based on their numbers. So for example, we can say this is, well, after manipulation, this will become this tree. A leaf node over here, internal node there, another leaf node here. And again, I'm using squares to represent leaf nodes and circles to represent internal nodes. I hope that's not too terribly confusing. And then 0 node, I just make an internal node because I don't know. So implicit numbering will go like this. We do 1, 2, 3, 3, 4, 5. Okay. So if we have 1, 2, 3, 4, 5, Okay. How do we know? Wait a minute. Is the not yet translated node, is it always going to be number 1 in the implicit numbering scheme? I have no idea whether the not yet translated node is a leaf node or an internal node. To me, it makes sense as an internal node, but I see that how it could also make sense as an external node. No idea. I'm just kind of like riding the line between the two, just somewhere in the middle. Okay, so we have this tree right here. And my question is, if we put the not yet translated node into the leaf nodes, right? Then we're going to have an external node of weight 0, the not yet translated node of weight 0, both in the list of external nodes, and that's fine. Yeah, it's always in the place of a leaf node, you're right. So I guess it would technically be a leaf node. But I don't want to confuse it with a leaf of weight 0, you know? Which is fine because all the leaves have characters associated with them, but that's beside the point. Okay. So, what do we need to do then? I will admit, I have not thought about this enough. So if you guys have suggestions, let me know. But the problem is this. I cannot quite figure out how to know where this not yet translated node actually is in our diagram. So let's go ahead and do something simple. We're going to assume that we're starting with nothing. The not yet translated node is the very start of our tree, okay? So let's go down here. We have the not yet translated node. So what we're going to do is we're basically going to move the not yet translated node such that it now has an internal node as a parent and a sibling that is an external node for the character that we're reading in. So we have extend node, and not only do we need Huffman tree, we also need a new, character. Yeah, character, new character key, I think is what I'll call it. Okay, so let's go up to the extend node function. Oh my gosh, extend node. There we go. Here, and we do character, new key. Down to the bottom. Okay. So we have the not yet translated node. Let's go through and let's do it. So we'll say we need a new node for the internal node. And what I'm going to do is I'm going to go here and go into the huffman.cpp file to make sure I don't accidentally create this incorrectly. So it looks like, one second, node parent is equal to new node. Yep. So we're going to do node parent is going to be equal to new node. Okay. Creating our new node. We're going to say node parent pointing to weight is going to be equal to 0 to start. Then we want node parent pointing to left is going to be equal to tree dot. Isn't the not yet translated going to be the only effective member of 0 block? Everything else should have at least 1. Yes, except for in the case, and this is where what I was trying to say before. There is a case here where we have multiple zeros. And this is the case that we have to, like, when we're moving things around, before we have yet incremented it, like right when we do the slide. So we always do slide and increment, right? So we always slide first and then increment. In that case, we have multiple zeros. And I'm not sure what to do about that. Now we could make it so the 0 block is, or the not yet translated node is always the last number in our, in actually both the internal and external node blocks. That's fine. I just haven't quite gotten a grasp on it yet, so I have to kind of think about it a little bit more. Anyway, let's keep going. So node parent left tree is going to be tree dot not yet translated. Okay, I guess that's fine. Now we do the following. We create, what do we want? How about node, I guess, key, node, oh, I don't know what to call it. How about we do node external? Why not? Sure. Let's do it. Equals new node. Okay. And we're going to say node external. Pointing to weight is going to be equal to 0. We say node external. One second. Node parent. Where did I define them? Yep. Let me go up here real quick. Node star. Node parent. And node external. Okay. Node external. Pointing to key is going to be equal to new key. And then we go down here and we say tree dot not yet translated, pointing to parent is going to be equal to node parent. And then we go here and say node external, pointing to parent. Needs more auto. I think it's fine. It's going to be node parent. Okay, so this is effectively setting all of these guys up. How to Pascal? How to? Hey, I've been working on a compression algorithm too. Ah, neat. Pants for birds. How have you been? Patrick OMG. How did the Pascal code treat it with a slide and increment? So I'll be honest, I'm not really able to read Pascal code so well, but maybe you are. So the code, the Pascal code is going to be available on, let me see, page 164 of this link, right? Shoot, I think I turned off my computer. Oh, I did. Dagnabbit. Yep. I will not be. Wait 1 second. Tree not yet translated parent. You'll also need a tree dot not yet translated parent left wait, why? Wait, Zadison, what you're saying is that I don't understand. So you're saying that the not yet translated node, which is on the left of the parent node, you want me to set the not yet translated node equal to node parent? Okay, let me go here. I apologize for this, but the Pascal code is here, I believe. Yep. Okay, so here's the Pascal code. It's on a page 160 something, 164-ish or something like that. I guess there's a lot of stuff we could do, but the parent of the not yet translated node will still have the not yet translated node as its left node unless you update it. The parent of the not yet translated node. Wait, but the parent of the not yet translated node should have, unless I'm missing something here, the not yet translated node as the left node. That's what I wanted. And yeah, Pants for Birds, there's a whole bunch of things we could do. However, we're kind of taking it one step at a time. So, I apologize for that. Okay. Let me see. Node parent, node external, new node. Oh, wait, really? Wait, what? You need tree, not yet translated, parent left. Okay. Should it not be this? Here, let me see. Tree dot not yet translated, pointing to parent, pointing to left equals tree dot not yet translated. Why would I be setting it equal to node parent exactly? This should be right, I think. Okay. Yeah, it always has to be on the left based on the algorithm. The not yet translated node is always on the left. Okay. So, and let me know if this is right. I think it's right, but I feel like you might be thinking something a little bit different than I'm thinking. So, okay. So what do we do next? Well, that line goes before the line setting its parent. 1 second. Wait 1 second. So you're saying tree, not yet translated, parent left is equal to node parent. Sure, I guess it doesn't really matter, right? So let's do tree dot not yet translated, pointing to parent, pointing to left, equals node parent. Switching 1 second. Let's just add in some quick comments here. What do we want? Creating new parent node. Going down here, creating new external node with given character. And down here, we're going to do, what do we want here? Switching, 1 second. I don't know what this one line is doing. It doesn't, the not yet translated node, sure, it'll have a parent, but all we're saying here is, I don't know. Okay, 1 second. Placing the not yet translated node on the left. Key weight. Oh, I forgot to do one thing. Node external here, parent, and then I need to do one more thing. Placing. 1 second. Not yet translated. And new external node on right. Screwed that one up real quick. On the left. And new external node on the right. Remember that the links between nodes go both ways from parent to child. Okay, so let's do this. Then we're going to say, what do I want? This is going to be node parent. Pointing to right is going to be equal to node external. Okay. No, my question isn't why we're updating. My question is, why is this node parent instead of tree dot not yet translated? That's my question. It's not why we have to link it back. That's fine. The question is why you wanted me to do node parent instead of not yet translated, if that makes sense. Okay. So node parent right, node external. Let me see. One second. Yes, you're totally right. I apologize for that. Okay. So, node parent, new node. We give it a weight of 0, and we say its left is a not yet translated node. That's fine. Not yet translated parent left is already not yet translated. You're replacing not yet translated, so it needs to be updated. What? No, here, let me just draw this out. Page, new page before. We have the following. We have the not yet translated node. Let's go here. Here. Not yet translated. Okay. We created a parent node, and we set this as the left node. Later, we set this as the parent node. That's fine. Then we set an external node, which I just called external. Here, and we set this as the parent. But you're saying not yet translated parent left is already not yet translated, but it's supposed to be not yet translated. Because not yet translated parent and then left should be not yet translated. Yeah, so when we set before you do your replacement, not yet translated already has a parent. Yes, it does. And then we replace it with the other parent. I guess my question is why just setting, why do we have to set? I don't understand why we need this line. That's what I don't understand. Because yeah, we're setting the parent. Yeah, I'm just not sure. It seems to me like without this line, it should be okay. Okay. So let me just make sure we have everything set. We have node parent equals new node. That's fine. We have node weight 0. That's fine. Then we have left tree. Not yet translated, that's fine. We have not yet created the external node for the right. What I probably should have done is created the right external node first. It's fine, it's okay. So now you node external, a new node. We give it a weight of 0. We give it the key. We set its parent to be the node parent. Yeah, but even so, okay, so this is that's exactly what I just did, by the way. So we do this. We have the not yet translated node. It has some parent over here. Okay, the first thing we do is over here, we create a new node. Oh, okay, I see what you're saying now. Okay. I was misunderstanding. Okay. I see what you're saying. You're right. So let's see. We need to. Yeah. Where are we? Node parent. Yeah. Okay. You're right. Okay. So guys. I'm obviously shot right now. There's some other things that we need to look into. However, it's 6:57 in the morning. We're at a pretty good stopping place here. We have this skeleton for the extend node function kind of written. We wrote the intree function. We kind of got started writing the vidder function. We're getting there. But obviously I'm completely shot right now. But thank you so much for coming in. I'm going to go ahead and end the stream here for now. Tomorrow we'll have a full 2-hour stream. Hopefully I won't accidentally turn off my computer in the middle of the stream. And hopefully I'll be feeling absolutely perfect tomorrow. But, you know, I'm not sure. Anyway, guys, thanks so much for coming in. Thanks, Addison, for all the help, and Gus Jordan when he was here, of course. Krabs, everyone for helping out today. It was great. And I will see you guys tomorrow for the next episode of Simuleos, where we continue working on the Vitter algorithm. I apologize for maybe moving a little bit slower than you would have liked today, but that's kind of how it goes. I let you guys know as kind of a disclaimer at the start of today's episode that it will be a little bit slower, but that's okay. Outside of that, have a fantastic day, night, afternoon, morning, evening, whatever time it happens to be your time, and I will see you around next time for the next episode of Simuleos, where we continue working on the Vitter algorithm, and we hopefully make some significant progress towards getting it written. And once it's written, we'll work on the visualization, which should take about a week, and then we'll be good to go from there. And then we'll start working on physics algorithms from there, and I'm pretty excited with the next algorithms we'll be looking into. Anyway, guys, thanks again for watching, and I will see you next time. Bye, guys.